So we'll start with the refresh of a single Gaussian. Our problem is we have a bunch of data points that come from a Gaussian. The Gaussian has a known standard deviation, but an unknown mean. Okay. So the data comes from a Gaussian with some unknown mean and a standard deviation of 1. The data is some x1, x2 through xn. And the question is, how do we find the maximum likelihood estimate of the mean? We did this together. What we did is we set up the likelihood function. The likelihood function of the data conditioned on the mean and on the standard deviation being 1. So what's the difference between these two? This is known and fixed, fixed and known. This is fixed but not known, and in fact this is what we're going to optimize over. We wrote this down as a product of the individual probabilities of each one of these x's because they're drawn independently. And we got rid of things that don't participate in the maximization, that don't depend on sigma. Remember that? And then we had a simpler expression, and we took the derivative, equated to 0, derivative with regard to mu, and equated to 0. And after doing all of that, so we said this was the argmax over all of mu of this. And after taking the log and taking the derivative, we got our result, which is the mu maximum likelihood is 1 over n sum of xi. Remember that? So we got this earth-shattering result that the maximum likelihood estimate is the sample mean, the average of the sample. But it was useful. Let's try to do the same thing for a slightly more complicated situation where the data comes from a mixture of two Gaussians. So graphically, there are two Gaussians. They have some overlap, as all Gaussians do. They have a mean. They should be the same height because they have the same standard deviation. They have the same width. I'm simplifying everything. They don't have to have the same width, but let's say they have the same standard deviation of 1. So they're identical, really. They're just shifted in space. This is mu A, and this is mu B. So this is Gaussian A, and this is Gaussian B. And let's say the data comes from them as follows. Every time you want to generate a single data point, you flip a fair coin. If the coin landed on head, you go ahead and sample a data point from Gaussian A. If it landed on tail, you sample a data point from Gaussian B. So the prior over which Gaussian you're going to use is 50-50. Again, that's not necessary, but I'm just simplifying so we can focus on the crucial parts. So my generative story is, let's say something I called H comes from a Bernoulli with probability 0.5. So it's flipping a fair coin. And if H goes one way, I draw X from the normal with mean A and standard deviation 1. And if H goes the other way, H is binary, I draw X from a normal with mean B and standard deviation 1. So this is my graphical representation of the process. The one other important thing is that each X is independent of any other X. Once I'm done generating one X, I'm going back to the top and drawing another H. So maybe I call this HI, and this is XI. Now that I have the graphical story, I can write down the likelihood function, which is the thing I would want eventually to maximize to find the maximum likelihood estimate. So my goal here is to find the mu A and mu B that maximize the likelihood of my data. Why do I write it like this? Because these together can be thought of as the lambda bar hat. Remember that lambda bar is the general term we used for an array of parameters. And our maximum likelihood, lambda bar, is the set of all the values that together maximize the likelihood. This is slightly more accurate than to talk about the maximum likelihood of this and the maximum likelihood of that, because the maximum likelihood of this might depend on the value of that. And the maximum likelihood of this might depend on the value of that. But I want to jointly maximize the likelihood. So this is my goal. Find this from data. From D equals x1 through xn. So I'm going to write here mu A, mu B, hats, maximum likelihood is defined as I'll write this a little higher. The argmax over mu A and mu B together. So think about it as a search in the joint two-dimensional space of mu A and mu B of the likelihood of the data. The likelihood of the data is the product I goes from 1 to n of the likelihood of each individual xi. How do I write the likelihood of each individual xi? Now I need to look at my graph. There's a 50% chance that this xi will be generated from mu A, and a 50% chance it will be generated from mu B. So this becomes 1/2 times the likelihood of a particular xi being generated by mu A. So that's 1 over 2 pi square root sigma. Actually, sigma is 1, so I don't need it. E to the negative xi minus mu A squared over 2. It's 2 sigma squared, but sigma is 1. Plus 1/2 1 over square root of 2 pi e to the negative xi minus mu B squared divided by 2. So now I have a well-defined maximization problem. Find the values. The xi are fixed. Remember, they are our data. They're fixed, whatever they are. There are two things that can vary here, mu A and mu B. And I need to find the value of both of them that maximizes this expression. I can use the same tricks I use in the case of a single Gaussian, which is, instead of looking at maximizing the likelihood, I can look at maximizing the log likelihood. It's the same thing because the log is a monotonic function. So this is argmax over mu A, mu B. The log of a product becomes the sum of logs. Sum, I goes from 1 to n, log. Should I have gotten rid of something first? I could get rid of all of this. Because these are constants. 1/2 and 1 over square root of 2 pi. They're constants and they're the same constants, so we can take them out of the summation and take them out of the maximization. They involve no mu A and mu B. So in this very simple case, I can just be left with this. Now I have log of e to the negative xi minus mu A squared over 2 plus e to the negative xi minus mu B squared over 2. What do I do next?
Differentiate.
Okay.
Really helpful, right? Because you have a product of his sum.
Right, but we can differentiate. I mean, it's true. That's the next thing I would do. So I would, well, maybe I'll write it here. I can say the derivative of the log likelihood with regard to mu A, and then I can separately do it for mu B. I need them both to be equal to 0 to find the joint maximum. Is derivative with regard to mu A of sum of log e to the this plus e to the that. I can try to push this further. It goes from 1 to n. This has to equal 0. Here we have xi minus mu a. Here we have xi minus mu b. And with regard to mu a, this part is a constant, actually. I can try to push it forward, but I'll get stuck. This is the point that you were making. I don't know how to solve this analytically. In fact, I believe there is no analytical solution. Compare that to what we did here. We got rid of this part. And then the log of this became the sum of this part. Xi minus mu, there's only a single mu, squared over 2. It was a very nice derivative, which gave me a quadratic equation in mu. Actually, after taking the log brought us to here, taking the derivative gave us a linear equation in mu. I can't do that there. My problem is that I have a log of a sum. And that's a very typical situation that I'll have when I have latent variables. Not necessarily. Latent variables can have all kinds of likelihood functions, but a very common thing that occurs is log of a sum, and we don't know how to handle log of a sum. We know how to handle log of a product, right? It's just sum of the logs. But log of a sum is tough on us. So I don't have a nice analytical solution the way I have here. So I have to resort to numerical methods of trying to find the maximum likelihood point. So I'll show you now a numerical method of doing that. Here's how we're going to do that. What should I start? I'll start by giving you the algorithm, and then we'll do the interpretation. For numerically maximizing mu A, mu B from data x1 through xn. Here's the algorithm. First step is initialize. Mu A of iteration 0 and mu B of iteration 0 to some distinct values. By distinct, I mean they are not both the same. That's the only requirement. So this is step 1. Step 2 is, of course, the choice of mu A and mu B that you had are probably not correct. They're just a guess, just a wild guess. But you assume temporarily that they are correct, and you ask yourself, given that they are correct, if they were correct, you look at each one of the xi's and ask yourself, which Gaussian is it likely to have come from, A or B? In fact, you don't try to give an answer A or B, you try to give a posterior. Given the tentative A's and B's, mu A and mu B that I have, and given a particular xi, how likely is it to have come from A, and how likely is it to have come from B? So that means that for every I, you calculate the probability that xi came from A. Conditioned on the current value of the mu's. Mu 0, A, and mu 0. Sorry, I won't make it 0 now, I'll make it I. What is my favorite index for iterations? K? I'm sorry, K. So I'll make it K. So now, obviously, the first step is the initialization step. This is an iterative step, so this is K. So probability that xi came from A conditioned on the current values of the things that I had a tentative assumption for. Well, what will this be? Using a simple version of Bayes' equation, I can write it as the likelihood of xi conditioned on, I'll just write mu bar, okay? No, likelihood of xi conditioned on, all right, yeah, but I want to express both the fact that it includes these and likelihood of xi, how do I write it? If xi comes from A, xi came from A, I'll leave it open. Normalized by likelihood of xi that xi came from A, and the likelihood of xi given that it came from B. Now, why did I leave it open? Because everything here is conditioned on the current values of mu A and mu B, which I will call mu bar K. So I have to put it here too. Mu bar K and mu bar K. So this mu bar K is with me everywhere. Everything is based on the assumption that these are the correct values, which we know is not the right assumption. But it's based on my current tentative assumption about the true values of mu A and mu B. If we lived in a world where mu A and mu B were indeed these values, there would still be uncertainty as to which A or B resulted in the current xi. Okay? So these conditionings are fundamentally different. This one is conditioning the parameter of the model.
Do there need to be sums over all the likelihoods?
Well, everything gets normalized if you... I didn't show you how this is derived. You can derive it as a joint. So it's the probability of choosing A times the probability of xi given A. But because the prior is the same, it boils down to just these two. If you don't believe me, try it yourself. I'm just showing you the simplest form of the algorithm. I want to stop and emphasize the difference. This is an assumption about the parameters of the model. And we're going to make this assumption in this iteration that they are exactly k, mu a k and mu b k. But even if you're completely right, and we don't need to make this assumption, that we know exactly the model, suppose somebody gave us mu a and mu b, and then gave us xi, we still don't know if that xi were derived from a or from b. There's still uncertainty. That's the latent aspect of things. So it's important to keep in your mind the distinction between uncertainty regarding value of parameters and uncertainty regarding latent events. In most formulations, they're very different. So let's look at the picture again of mu a and mu b. Let's say you are an outsider and you know exactly mu a and mu b. Sorry, this is a and b, and the value here along the x-axis is mu a and mu b. So you know everything there is to know about the model. You know the generative story complete with the correct value of the parameters. The mu's, the sigmas, everything. The priors, you know the model perfectly. Somebody gave you xi. You still don't know whether it came from A or from B. It could have come from either, right? Now, you can guess or you can estimate that it's more likely to have come from B than from A. Certainly, if it were here, it's much more likely to have come from B than from A. Why? Because you can see that A has a very, very low likelihood here. And the equation I wrote here is exactly the height of that likelihood. It's the likelihood of xi under the assumption that it comes from A divided by the sum of the likelihood. So it is the height of this divided by the height of this plus the height of this. In other words, the relative fraction, that is this versus this. And you can see, because the Gaussians are identical and just shifted, that as soon as you are more than halfway between mu a and mu b, b will dominate on this side, and if you're in this direction, a will dominate on this side, and the halfway point is exactly where they're the same, in which case the answer would be 50-50. It's as likely to come from A as it is to B from B. And what you may not see in the naked eye, but you can derive arithmetically, is that as you go further and further, the ratio becomes more and more severe. It becomes more and more certain that it came from B. So, in fact, I can write it here. This is the height of the one likelihood thing divided by the sum of them. And this boils down to e to the negative xi minus mu a squared over 2 divided by e to the negative xi minus mu a, the same thing, squared over 2 plus e to the negative xi minus mu b squared over 2. This and this are the same. And this is only differs by having a mu b instead of a mu a. So you can, I'm sorry, I forgot to say that this mu a is the kth version, the kth estimate. So given the kth estimate, if you pretend for a moment that that estimate were true, you get the posterior probability that for every xi that it came from A. And of course, 1 minus that is the posterior probability that it came from B. You calculate that for every I. What you're effectively doing is you are taking each xi and you fractionate it. You break it into two parts. If xi were exactly in the middle between mu a and mu b, you pretend that there are two halves instead of one xi. Two halves of xi. One half was generated from xa, and one half was generated from xb, from Gaussian A and Gaussian B. In fact, I have colors. So I will use red and blue for A and B. Here's A, here's B. Now xi is going to go. Let me now keep counts of how many of the x's came from each Gaussian. What came from A and what came from B. So this xi came half-half. Of course, that's not true. It either came from one of them or it came from the other. What I'm saying is that I'm using my posterior estimate based on my current estimate of the mu's to say how likely it is to have come from A and how likely it is to have come from B. And these two have to sum to 1. Now this xi clearly is much more likely to have come from B, so it would look like maybe 0.1 and 0.9. I'm sorry, 0.1 and 0.9. This is half. And some x that is on this side might be 0.8 and 0.2. And there may be one that's way out there, in which case it's 0.999 and 0.111, 001. So you can see these are pairs that sum to 1. So what this step does is it calculates the fractions for each one of them. And now comes step 3, which is I'm going to use my fractional data that's red to re-estimate the mean of mu A. And I'm going to use my fractional data that's blue to re-estimate the mean of mu B. How do I re-estimate it? The same way you estimate mean here, just the average of the points, with a slight modification that the points are now fractional. So I need to take every point into account fractionally. Only half the point, only 10% of the point, only 90% of the point. So what would the formula be? Mu k plus 1 A, so that's my k plus first estimate, that's the next version of the estimate, is equal to the sum. I need a name for this fraction. Should I give it a name or should I just write it as it is? Let me just write it as it is. I'll rewrite. Now you need to see this. Thank you. It's one of the many reasons to have TAs. Thank you. So step number 3 is the new, namely the k plus first or k plus 1 estimate of A is going to be the weighted average of the fraction data points. And the weights are going to be the posteriors. So I'll call them Wi for now. WIA times xi. Sum I goes from 1 to n, and all this is normalized by the sum of I goes from 1 to n of WIA. Right? These are weights. Xi's are the points along the x things, and I'm going to average them, mean them, but weighted by what fraction was assigned. And the WIA is defined as the probability that xi came from A given the current estimates, mu A k, mu B k. This is also the posterior assignment of the latent variable hi. So remember in our picture we had this latent variable hi, which took the value 0 or 1. In fact, it could have taken the value a or b. So another way to write this is that the weight is the probability of hi equals a, given the current estimates. Okay? So this was our third step. Bring it down here. So it's wi xi divided by sum of wia. It's the same thing as here. And the mu b of this iteration is the same thing, sum of wib xi divided by sum of wib. The one shortcut is that wib is just 1 minus wia. So we don't need to recalculate it. We calculated for one of them, and the other one is 1 minus, because they sum to 1. In fact, I should have used, right? So what did I do? I started with some arbitrary mu's, and I ran through one iteration and got some new mu's. I'm going to iterate it. So I'm going to, from step 3, move back to step 2, and from step 2 to step 3. So I start with k equals 0, and I use it to generate mu's for k equals 1, and then I go back to here, and back to here, and back to here, and I'm sorry, back to here, to here, to here, to here, iterate between them. So I keep generating mu's, pairs of mu a and mu b that go from iteration 0, 1, 2, 3, 4, 5. Now the important and beautiful property of this algorithm is that in some sense the mu's are guaranteed to get better, no matter where you start. And in fact, for this particular problem, no, it's not true. They're not guaranteed to end in the same place. But they are guaranteed to get better, and under some conditions they will converge to a local maximum. Question?
What if by some incredible chance of fate you start with mu a and mu b such that they are already the global minimum?
Then the next iteration will come up to exactly the current iteration. It will be a, what do you call it, a no-op. It's a stationary point.
But because you have an uncertainty in the way xi's are generated from whether mu and mu b, the weights will not be the same. I'm not seeing how they will, the values will not be updated.
Maybe we should do a simple example. Let's start with, here's the x-axis, and we have a point at 3, a point at 5, and a point at 7. So we have x1, x2, and x3. And let's say we started with mu's, mu a of iteration 0 at 4, and mu b of iteration 0 at 6. Now, why would you start in such a symmetric thing? The answer is you don't have to. In fact, we can start with it at 7 if you prefer. Let's start it at 7. I don't guarantee you that we'll get nice results. The numbers are going to be funny, but we will get a general idea. And of course, you can start with it anywhere. You could start with it here, Although you could argue that you know that the end result would be inside x min and x max, so there's no point in starting there. But you could start there. So let's say xb is 7. And let's see how these different points are attributed to A and B. So we have A and B, and A is red, and B is blue. And here we have the xi's. This is I, so this would be 3, 5, I'm sorry, I is here, I and xi. 3, 5, 7. This is I, so this is 1, 2, 3. I goes from 1, 2, 3. The values of xi goes 3, 5, 7. And mu's start at 4 and 6. Where would 3 be assigned? The only thing that matters is the distance here in units of standard deviation. Right? Standard deviation is 1. So really, this would lead to e to the negative 1 squared over 2. Let's say that our sigma is 1 over square root of 2, such that 2 sigma squared equals 1. Okay? So I don't need to worry about the 2 here. Here it's e to the negative 1, whereas how likely is 3 to be generated from A? Well, it's proportionate to e to the negative 1. How likely is it to be generated from B, which is 7, is proportionate to e to the negative 7 to 3 is 4, negative 4. So there's a huge asymmetry, and the vast majority of point number 3 will go to A. So A would be e to the negative 1 over e to the negative 1 plus e to the negative 4, which is almost 1. And this will be e to the negative 4 over the same denominator, e to the negative 1 plus e to the negative 4. What would be the situation with 5? Here you have 1 standard deviation from 5 to this mean, and here you have 2 standard deviations. Now the proportions are not going to be so bad, right? It's going to be e to the negative 1 over e to the negative 1 plus e to the negative 2. And this is going to be e to the negative 2 over e to the negative 1 plus e to the negative 2. And finally, in 7, this time B will be the winner. It will be e to the negative 0, e to 0, over e to 0 plus e to the 4 to 7 is negative 3. And here it's e to the negative 3 over the same denominator. So what happened to us with A? Roughly how much this is? I'm sorry? 0.95. Thank you. Another reason to have it TA. 0.95, which means this is 0.05, but let's focus on this. What's this? It's the most moderate. It's probably 0.7, 0.8.
Yeah, 0.7 or something less.
0.7. Just common sense. If this is red and this is blue, and the standard deviation is 1 unit, we're looking at this number here, x2. It is 1 standard deviation away from this one. It is 2 standard deviations away from this one. So there's a factor of e in there. So 0.7 divided by 0.3 is maybe a factor of e, about. And finally, 7 is biased towards B. So the point is right here, right in the peak of the Gaussian. E to the 0 is 1. So it's 1 over 1 plus a very small number. What's e to the negative?
It's like the first point. So
Really? Oh, because it's a difference of 3?
yeah.
Okay. So this would be 0.05. Oh, this one is the 95, and this one is 0.05. So now we are re-estimating. I'm going to get back to your question. We're re-estimating A, the mean of A, based on 95% of 1 point, so almost a full point sitting at 3. So let's say almost a full point sitting here. Let's say this is 1, but I'm only going to go to 95%. 70% of a point sitting at 5. 70% of a point. This is about 0.7. This is about 0.95. And 5% of a point sitting at 7. It's going to be tiny. 0.05. I'm looking for the mean of these. And the mean is going to be, where is it going to be, do you think? Is it going to move to the left or to the right? So I think it's going to move to the left. You can calculate it, of course, but let me tell you my reasoning. I start looking at the blue one, and the blue one I'm sure would move to the left. I'm sorry, then it has to move to the right. Huh? Well, let's do the logic together. But let me convince you first that the blue one will move to the left because all the points are to the left except for this point, which is right on it. So it gets pulled by some amount to the left. So this will move to the left. Now I know that the center of gravity of both of them has to be the same. So this one has to move to the right. And by the same amount since the priors are equal. Now convince me that it's true. It's not trivial. I mean, this is a larger column than this one, but there's a column here that's further out. You're not sure?
I don't think the center of gravity has two sums to the same amount.
You don't?
Yeah, because they are normalized by difference.
So center of gravity does take into account.
No, if they were both arbitrarily to the right of the true
Uh-huh.
values, wouldn't the center of values be pulled?
You're right. They would be pulled in. Maybe that's true only after the first iteration.
It's because the new mu a will be the sum of WIA times XA divided by this thing, and the new mu b will be divided by a different thing. And the center of gravity is the numerators added together divided by the denominators added together. So there shouldn't be a constraint that they should sum to the same.
So my intuition is still that after the first iteration, they should move in unison, either both in or both out. I could be wrong. Let me think about it.
For example, if you started with both things.
Right, that's the example that
Yeah.
was given here, but that's the start point. So the initial values could be anything. But after the first iteration, it's just intuition. I will try to beat it out of me or beat it into you.
True to me. But anyway, I
Okay.
calculated the new mu a, which is 3.94.
3.94. No, this doesn't contradict it because this is the first iteration. But 3.94 is moves a little bit in this direction.
Yeah.
Okay. Definitely not true for the first iteration. You convinced me already because you could have started God knows where. Yes?
If the centers of gravity are always the same after the first iteration, wouldn't all the means always converge to the same mean?
No. So suppose you had a lot of data and it looked like this. Lots of a cluster here and a cluster here. Then you are likely to converge to one mean here and one mean here.
So then the centers of gravity are different.
Oh, no, I'm not saying that they are converging towards the same center of gravity. I am saying that some combination of the centers of gravity I think is invariant. But this is only intuition. Don't rely on it until I tell you that I proved it, or that it's not true. You expected this what would happen because this would explain the data well, right? Anyway, trying to go back to your question, which I forgot by now.
I think I see the answer from
Okay, good,
If
good.
you started with 4 and 6, then you would get the same weights in A and product B, and your update would be used.
Yes, if you start with a symmetric situation, you will continue with the symmetric situation. So that's the example I wanted to do, a 4 and a 6. And then it's exactly symmetric, and they will not necessarily stay in the same place, but they will move in tandem because of the symmetry of the situation. We can try that.
Is it true to say that means could, in a very limited circumstance, meet, but they could never cross? So if
Um,
it starts to the right, it could never shift to the left of A.
Well, they could cross on the first iteration because you can arbitrarily. No, they won't. No. There's no reason.
They have the same standard deviation, they won't.
Right. All under the assumption of same standard deviation and equal prior. That's the only condition for which I have somewhat of an intuition. Then I believe they will not cross. And meet. Will they ever meet?
No.
I don't think so. Because you can always get a better likelihood by... So if there's a single data point, yes, they will meet on that single data point. If there are 2 data points, then each mean will gravitate to that data point. If there are more than 2 data points, I believe they will not meet.
So what if the true distribution is just a single?
If the true distribution is just a single mean and you have a lot of data, that is a very good point. Because, okay, let's think about it. Suppose the true distribution is that mu A equals mu B. And suppose you have a lot of data. Is it the case that the highest likelihood will be achieved mu A equals mu B?
But that's just like a clustering problem, right? Like, if you force yourself to have 2 clusters, you anyways will have 2 centers which are slightly off within the mean.
Mm-hmm.
So I don't think mu A would be equal to mu B, but you still will have the EM spaced attempt to describe the data with 2.
I think you're right. I think that for any finite sample, the maximum likelihood solution would tend to be at some distance, right? But that distance will grow smaller and smaller and smaller as your sample size grows larger and larger. That's my belief.
I tried that. The difference is small.
Yeah, just like in clustering, when you try to separate a cluster in 2, you get some arbitrary distance between them. They're highly overlapping, but there's some distance between the clusters, just like the point you made. Yeah, Malcolm.
So what's the institution, or not institution, but intuition as to why the clusters will never overlap, or the means, like the distribution of the means will never overlap? Or I guess when we say overlap, what do we...
No, they don't say overlap, they say cross.
Cross.
That means when you start with mu A here and mu B there, and then after one iteration, at some point they switch. Which one is larger, which one is smaller. So there's no question of overlapping. There's no distribution of mu's. This is not Bayesian statistics. This is single point. We're trying to derive a maximum likelihood. So at any one time, there's a single point estimate from mu A and point estimate from mu B. But they change over time as you iterate through the algorithm. And they converge to some values.
But it would never make sense when we cross.
I think not. My intuition says no. If one of you can come up with a quick proof, that would be nice.
Yeah, because for each point, so how do I say it? The points on the right will have a larger W for the cluster B, and points on the left will have a larger W for point A, for the cluster A.
Mm-hmm.
Therefore, when you take the weighted average, the points on the left will have contribute more to cluster A.
That convinces me. Yeah. Another way of saying the same thing is as you move through the points from smaller to larger, if you sort of the xi's in order, you assign higher and higher proportion to B, to whichever one was on the right first. And therefore, its mean, it's the difference between the two means will, continue to be positive. It's not that important because the definition of A and B are somewhat arbitrary. Which one is A, which one is B? In fact, if you started with the reverse assignment, you'll end up with the same solution, only you would call one A and one B. What is important is that there is not necessarily a single solution. So the likelihood space is not necessarily convex. It may actually be convex for this particular case, but the general problem of, no, it's not even convex for this. Yeah, because there are at least a permutation of solutions. If mu A is this and mu B is that, if you swap them, that's another maximum likelihood, right? After your algorithm converged, if you change the names of what's mu A and mu B, you got an identical likelihood value. So that's at least two solutions. Now we can generalize this to many other, in many other directions to the case of mixture of Gaussians. We can make a number of Gaussians larger than 2. We can make it any finite number. We can make the variances varied, and they could be just different, one of them 1, one of them 3, one of them 7, or they could be unknown, and we're trying to maximize jointly not only the means but also the variances. And the other thing we can change is the prior. The prior doesn't have to be 50-50, it could be 40-60, or again, it could be a parameter that is jointly estimated. So the most general mixture of Gaussian maximum likelihood problem is lambda is the set of mu A, mu B, I'm sorry, it's not A and B, it's mu 1, mu 2 through mu L, sigma squared 1, sigma squared 2, sigma squared L, and prior, I don't know what to call it.
You already used W for the prior.
I use W?
Yeah.
Where did they use W? That wasn't for the prior. W was the posterior.
Oh.
I really should use little lambdas, I think. Usually we use lambdas, right? Like in linear interpolation. So I'll use lambda here. It's different than this one. These are little lambdas.
We use beta for the entire set of parameters.
Beta?
Yeah.
Okay. I like beta because I usually know how to draw it. Theta? Oh, okay, theta. Lambda 1, lambda L. So this is the set of 3 L parameters, where L is the number of components. And our problem is to find the maximum likelihood of this set of parameters, namely the point in 3L dimensional space that corresponds to these parameters. It's defined as the argmax over all possible values of theta of the likelihood of the data x1 through xn given theta. Right? That's the general form. But this likelihood is now pretty complicated. It is the sum of lambda I, j goes from 1 to L of 1 over 2 pi sigma j e to the negative xi minus mu j squared over 2 sigma squared j. And all of this is the likelihood of a single point, xi. So now I need to take the product of all of this. I goes from 1 to n. Now look how many parameters I have here. I'll use orange. These are parameters. These are parameters. These are parameters. All the things with the j are parameters. The xi's are fixed. And now my question is, given a set of xi's, derive the 3L parameters that maximize this expression. And the thing to remember is that there are many local maxima. In fact, there may be even solution where the likelihood is not bounded. In fact, it's usually not bounded if you don't bound the sigmas. To see that, let me give you a solution that gives you arbitrarily large likelihood. Suppose you have lots of xi's, x1, x2, x3, x4, etc., x5. I'm going to choose one of these xi's and one of the Gaussians. I'm going to position my Gaussian right above. Let's say I chose x4. I'm going to position my Gaussian right above x4, and I'm going to let the variance or the standard deviation of this Gaussian shrink down to 0. As it shrinks down to 0, the Gaussian becomes more and more peaked. So I can make the likelihood of this particular data point arbitrarily large, unlimited, by shrinking the sigma to 0. And it's enough that I made this particular component arbitrarily large. I can just use another Gaussian to capture everything else, not in any particularly nice way, just a broad Gaussian that accounts for everything else. And now I use two Gaussians, and I got infinitely high likelihood. Okay? And I can do that for any one of the data points. So each one of them represents a cone, an infinitely growing cone in likelihood space. So a solution, a region, a singularity region where the likelihood function is unbounded. So the likelihood space is very complicated, and it could easily go to infinity unless you restrict the sigmas. If you say sigma cannot be any less than some amount, then the likelihood space is bounded, but there still could be multiple maxima. Yes?
So here we consider A and B to be the hidden variables, or is it the parameters that we're talking about?
The latent variables are, there's one, in this case, there's one latent variable for each xi, and it is hi, namely whether the xi came from A or came from B. I cannot overemphasize the importance of distinction between the parameters, which are just the mu A and mu B, and the latent variables, which are the hi's. It's a different level of not knowing. Parameters not knowing is overcomable. You can, with enough data, and with enough computation, you can estimate them well. Or you can ask somebody who knows them, or whatever. The latent variables are inherently unknown. And even when you know everything there is to know about the model, you still don't know the latent variables. If you knew the latent variables, finding the maximum likelihood solution would be trivial. To make that case, let's pretend that we know the latent variables. I still want to leave this here. So let me do it here. xi, so I, xi, and hi. I is 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say we have 10. Can be as many as we want. Xi's, I don't have to order the xi in a particular order from left to right, but I usually do it just for simplicity. They could be in any order. I don't know, 0.1, 3.5, 7, 10.1, 12, 15, 35, whatever. Now, let me not put them in order. I deliberately do not want to put them in order. 1, this will be 2, this will be 12, 4, negative 1.5, and 27. Now, suppose somebody told me the secret. Somebody looked under the hood and told me which Gaussian they came from. Not surprisingly, the small numbers tended to come from Gaussian A, and the large numbers tend to come from Gaussian B. So hi would be A, 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 A. This was B, 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 B. What do I do now? I take all the points that came from A and I color them red. Sorry, it's not red. 1, 2, 4, and negative 1.5. And I take all the points that came from B and I color them blue. 7, 10.1, 12, 27. I might have surprises. Let's say I have a point 8 here. And I would have thought it's large. In fact, it's larger than 7. But when I find out it actually came from 8, that's a surprise. But since I know it, I'll paint that red. Now I can calculate a maximum likelihood estimate for mu A just by looking at the red points. So I was able to separate the problem into 2 separate problems, each one of them very simple. Estimating the mean of the red distribution, estimating the mean of the blue distribution. All right, so mu A, maximum likelihood, would be 0.1 plus 3.5 plus 1 plus 2 plus 4 plus negative 1.5 plus 8 divided by 1, 2, 3, 4, 5, 6, 7. And mu B, maximum likelihood, would be similarly the sum of these divided by 4. In fact, I could extend my solution to cases where I don't know the standard deviation and I don't know the priors. I could estimate the prior on A to be 7 over 7 plus 4, right? 11. The relative fraction and the standard deviation of A to be an estimate based on the standard deviation of these numbers. So I basically separated it into 2 separable problems, red and blue, if I know the true assignment. My problem is that I don't know the true assignment. What I'm doing is I'm assigning these fractionally to A or to B. In my original algorithm, I'm using posteriors. So what I want you to focus on for the rest of our discussion is this thing. The posterior probability that a given data point came from A, or more generally, the posterior distribution over the latent variable. In the general case where you have more than 2 Gaussians, you have k of them, I will have 1 random variable for each one of these component Gaussians, and it would be the likelihood that that component is the one that's chosen. So let me do that. I'm going to slightly change the notation. Let's say I have L Gaussians, uniform prior, namely lambda 1 equals lambda 2 equals lambda L equals 1 over L, and sigma squared of k is 1 for all k. So I still know the standard deviation and I know the prior, but I have k components. Now I have xi it has some values, x1, x2, x3, xn. This is the observed data. I'm going to define a set of L random variables. In fact, it's L families of random variables. They're going to be Z Ji. Zji is defined as a simple indicator variable that can take on the value 1 or 0. It is 1 if and only if data point xi came from component j, from Gaussian j. Xi came from j, and it's 0 otherwise. So I will have Z1i, Z2i, all the way to Z Li. How many Z variables are there? As many as there are Gaussians times number of points, L times n. Each one of them is a single, simple binary random variable, 0, 1. To somebody who knows the truth, who has seen the latent variables and knows each xi, which Gaussian component it came from, they will know which in this column is 1 and which are 0. In fact, we all know that in every column there's exactly one that is 1 and all the rest is 0. So the summation here over all the z's, summation over the z's, is always 1, 1, 1, 1, 1, 1. But we don't know where they're hiding. We don't know where the ones are hiding. And now my algorithm can be written as initialize the mu's, mu1, I cannot call it A and B anymore, it's mu1 through mu L of iteration 0. And now what I'm doing in the next step is calculate the expected value of each Zi. That's what this is. It's the probability that Zi is 1. But for random variables that are just indicator variables have value either 0 or 1, the probability that they are 1 is the same as their expected value. Is that clear? If you have random variable Z, which takes on value 1 with some probability p and value 0 with probability 1 minus p, then the expected value of Z is p times 1 plus 1 minus p times 0. So it's p. So probability that it's 1 and its expected value are the same thing. So now I'm going to, this was my step 1. My step 2 is calculate the expected value of Zji given the mu's of iteration k. And step 3, I'm just rewriting our algorithm, generalizing it to a large number of Gaussians. What was step 3? We derived new estimates for the mu's. How did we derive them? We derived them as something that looks like a relative frequency estimation based on fractions of points. In fact, you can show that this estimation is the maximum likelihood estimation if indeed you had these many points. So if you pretend that these are not probabilities, but together they are a fraction of a point, the maximum likelihood would be just a relative frequency. So the general rule here is that the new mu j of iteration k plus 1 is the one that maximizes Do I want to write maximizes the likelihood? Yes, let me do that. Is the one that maximizes over all mu vectors the likelihood of the data conditioned on assuming that these z's are fractional. And I realize that what I'm saying does not sound as clear as it should be. So let me think of another way of saying it. When we get to the EM itself, I will redraw this and it will be clear. It is maximizing the likelihood of the data conditioned on assuming that the zij's are the expected zij's. And that's the best I can do right now. So under the assumption that as if the real zij's are 0 and 1. But if we had made the assumption that they are not, that they are fractional, and their fraction is proportionate to the expectation that they are 1. So we're substituting the expectation of z for summation over the possibilities of z. That's maybe a better way of saying it.
Essentially what you're saying is instead of having an extremely peak distribution over one value, you have some sort of a distribution over all the possible values of zi in one column J.
What I'm saying is that there is an expression that I can write for the total probability of the observed and unobserved variables, the zij's and the xi's. And I can try to maximize over that. Instead, I'm maximizing over the observables only, conditioned on the unobservable, the z's, being at their expected values. So now is the time to switch to the formulation of the real EM. And now we ran out of time. So I will come back to this. I apologize if I confused in the last 2 minutes. I guess all I want out of this stage is just a rough intuition of the iterative step involved. Then we're going to go to the EM itself, and we will do it more formally. I should also mention that this kind of explanation with substituting the z's only works for some subset of EM, specifically when the likelihood function is a member of an exponential family. We will go over that as well, what that means. For most cases we deal with, they fall into that class so that we can derive EM very easily that way, but we will also discuss EM in general, not relying on that. All right, so I'll see you on Wednesday.